Welcome. Thank you all for attending today's talk. Today we're going to talk about Zenseact's journey to developing self-driving cars with OpenShift. My name is Dan Knoll. I lead product management for Red Hat's in-vehicle OS team, and my colleagues Janne Janssen and Johnny Westerlund are going to present. This is Johan Janssen, and Johnny Westerlund will present the bulk of the material around what Zenseact has accomplished. And I'm going to try to frame the discussion to start with how we think Zenseact fits with Red Hat's strategy in automotive more generally. So this is a quick introduction. The automotive industry is undergoing a rapid transformation, all kinds of disruption impacting the automotive industry, not only from autonomy, but from things like electrification and to the achieving what we are calling in the industry the software-defined vehicle 4.0. And on that journey, we're taking different steps kind of on the features and functionality vector towards achieving what we want to achieve with software-defined vehicle, where you have long-term value and relevance, where cars are updatable in the field for a decade or longer, where I'm introducing new features to cars as they are deployed in the field over time, and I accomplish mobility as a service as a standard feature in cars. So let's think about that as we talk about what Zenseact is doing. So this slide kind of puts in perspective where Red Hat is and what the edge is and where Red Hat plays. In this kind of circular diagram, in the upper left, we have the enterprise edge, which are second and third tier data centers where Red Hat's standard products that you know and love play today. In the lower left, the provider edge, which is dedicated towards telco data centers and owned compute infrastructure. And you've talked about that at this conference and at other conferences about what Red Hat is doing there. The automotive side, the in-vehicle side, is on the right side of this diagram, the engagement edge, where these are traditionally proprietary and bespoke solutions leveraging embedded computing, and where Red Hat is trying to introduce standardization and Linux as a standard-based offering into these distributed systems and edge compute systems. And we're going to talk a little bit more about that as we go in the presentation. The in-vehicle software architecture is an interesting journey. Zenseact is going to talk today a lot about what they're doing in the cloud in order to prepare their solution to be deployed into the vehicle. On the left side of this diagram, we have kind of a traditional or legacy car that has a lattice of ECUs and kind of complex interconnects, where one application resides on one physical ECU and where I have a very tight connection between hardware and software. And in the move towards the software-defined vehicle, which we've introduced already, that concept, the network in the car becomes simpler. I virtualize functions to run on high-performance computing platforms that run together rather than in a distinct fashion, and my software-hardware architectures become disconnected. This is where we're introducing a new operating system, the Red Hat in-vehicle operating system, and what I'm working on today. But what we're going to talk about in this session is going to focus on the software that is being developed in the cloud to be targeted to an in-vehicle solution in the future. This talks about, what about differentiation? So Red Hat is about open source, standardization, collaboration of communities. And with that being the foundation of a pyramid, we want to eventually, at the peak of the pyramid, enable an ecosystem where OEMs, automotive OEMs in this industry, can introduce unique selling propositions, unique value, and drive the profits out of the industry that they want to achieve. And then in the middle, we're going to see the industry collaborate on middleware-based solutions and standard architectures that run on top of underlying open source and operating systems in order for their differentiation to emerge based on standardization and minimizing their cost and decreasing their time to market. So Red Hat's focus in the software-defined vehicle is kind of a complex lattice. On the left-hand side of this diagram is the in-vehicle portion, which my team is working on very hard. We'll introduce that product in the future. We're addressing the automotive industry, and automotive OEMs have different types of software that can connect to the vehicle and that also interface with the cloud. On the top, we have the development and testing activities that OEMs have to go through in order to deploy the software that resides in the cloud and in the vehicle in order to deploy their vehicles. In support of that, they have connected platforms and operation centers that actually interface with fleets of cars on the road to do things like software update, diagnosis, monitoring, these type of functions. And then of course, OEMs are manufacturers, so they have traditional IT and all the type of operational technology that supports their manufacturing and of course the traditional business lines. And all of those leverage cloud components. And as we know, Red Hat is in this business. So what are some examples of focus areas and references that Red Hat has that support these needs by our OEM customers? So in the in-vehicle portion on the left, last year we announced our partnership with General Motors and our partnership with an important SoC provider, Qualcomm. Look for more news about our in-vehicle OS solution in the coming months and quarters. But on the top row, in the development and testing, we're working with a number of automotive manufacturers, including Volkswagen for virtual testing, Zenseact, who's going to talk to us today about CI/CD and software factory based on OpenShift, and Ceph with their ADAS data bridge. Those are exciting reference examples that we'd love to tell you more about. And you're going to hear a lot today about Zenseact. In the middle, with this connected vehicle platform and operations center, we're working with customers like BMW, obviously a well-known German OEM, and Luxoft, an important system integrator who works in the automotive space extensively with global OEMs, and Tata as well. On the lower, supporting the IT manufacturing and traditional business lines, we have success stories with Audi, with Volvo AB, and with Ford, focusing on cloud and developer productivity. These pursuits are leading us to define and to work with our partners in defining solution blocks that help contribute to these larger functional areas. On the top, this thing we're going to talk about today, the pursuit of CI/CD, virtual testing, digital twin, the idea of doing extensive amount of testing for automotive applications in the cloud, leverages some of these elements we see in the upper right. And Red Hat is working to develop this IoT blueprint and vehicle simulator, and this notion of test infrastructure as a service. For the second block below this pursuit connected vehicle, we have functions like over-the-air update and kind of this automotive cloud that can act as this connected vehicle platform and operations center. And we have a connected vehicle architecture that we defined there. And these are offered as blueprints and validated patterns which are available on GitHub. So we want you to talk to us about these. If you want more information, there's a GitHub reference or hybrid cloud patterns reference that you can see and research on your own. But that's enough of setting the table. I'd like to hand it off to my colleagues to present details about Zenseact.
Thanks a lot. Can you hear me well? No? Okay, then I'll take Test. Yeah, that works better. Hi everyone, hope you're doing fine. So yeah, let's talk a bit about Zenseact. We're a company based in Sweden, Gothenburg, and we're focused to make autonomous vehicles. So each year, 1.4 million people die in car accidents each year. And about 50 million of those are badly hurt, resulting in a lot of pain and suffering and staggering material costs. And in the US alone, around 6,000 pedestrians are killed. And about 80% of these accidents occur in the dark. So that's why we're here, to save lives and make roads a whole lot safer. We're an AI company committed to transforming the automotive industry. And our mission is really to end car accidents. Now this is a really ambitious purpose and going to require some super advanced software. Thank you, Johnny. Changing the slides, perfect. So, I mean, the car must be able to handle a lot of difficult situations and whatnot. For instance, it must be able to see far ahead to be able to react in time. It needs to be able to keep a safe distance, and it needs to be able to do this in high speeds. Thank you, Johnny. And of course, it must be able to handle this in the darkness. Now, remember, darkness is really the villain here. And so this is really what the LiDAR-equipped car, how that perceives the reality. As you can see, it's far better to see the reality than the human eye is. And being based in Sweden, we get a whole lot of darkness practice, really. Seeing a Swedish person laughing right here. That's great. Of course, you must be able to identify a whole lot of weird objects, not even at the roads, but such as cars or traffic signs or whatever, but even stuff all around. And you must be able to handle unexpected situations. So it also must be able to sense and react quickly and make the right decisions fast. So this is just an example of what AD must be able to handle. Simple solutions can't, but ours can. We use unsupervised driving technology in today's supervised driving. It's not overkill, it really just makes it a whole lot safer. So this is the sensor blueprint in a Volvo car. And as you can see, there's a lot of hardware going into it. It must be able to have eyes and to take in the visual world. So there's lots of different cameras and radars to it. So there's a lot of hardware going into it, but this does not really mean a whole lot without the brain, meaning the software in the car. And that's how we help this bad boy, the Volvo EX90, get up on the road nice and safe. Now, of course, the secret is, of course, then in the software. And fortunately today, the safety features in today's cars are within the software. And that's really how we can make cars a whole lot safer, faster. And that's Zenseact's motto, towards zero faster, really. So let's take a bit closer look into how we do it, and more specifically, first looking at a bit of overview of Zenseact's development loop. So it all really starts at requested data from our engineers, and which will later end up in an over-the-air update car. And as you can imagine, the more efficient we can make the software loop at Zenseact, it will have a huge impact in our development speed. So let's take a closer look at this. And we're going to be talking a bit about OpenShift journey, and really a lot about optimization within our CI/CD and general workloads such as GPU workloads as well. And really, the theme is really to be able to increase our input with kind of not adding any more hardware or anything.
Yeah. Can you hear me okay? Is it working? Check. Yeah, okay. Hi, everyone. So the starting point for this journey was 4 years ago now, 2019. The introduction was really, or the starting point was really the usual RFX, the RFIs, the RFPs, the RFQs, and whatnot, where we got a list of capabilities or requirements that Zenseact needed to fulfill, and we did a lot of back and forth, discussions, demos, workshops, etc., etc., etc. Which kind of like ended up with you selecting us for the partner of this journey, and the starting point was really sending a consulting team from Red Hat Services on the ground to help you get that initial cluster up and running. And I remember that the team was really excited because you have quite a unique culture at Zenseact, which they were really excited about. So go ahead. More. Oh,
Need a mic. Yeah, I mean, we all set it up because we kind of realized that we needed to run our workloads a whole lot more dynamically. We needed to remove any lead times or handovers, if you will. So that's why we kind of look to adopt the cloud-native ecosystem a whole lot more. We're really able to put our developers in the driver's seat. So looking a bit at our challenges, as you can imagine, like our CI/CD flow is really, really important and something that we measure a whole lot, and really where we try to make a lot of improvements. Being a software company, as you all might know here, the CI/CD parts are really, really important. And at Zenseact, we have really unpredictable workloads, very, very spiky. So they're really hard to predict, and we typically find ourselves in situations where we didn't have enough resources. And we did kind of find out that we didn't have any capacity issue, it was more so of a resource provisioning issue. These situations led to a lot of queue times within CI. Now, as you can imagine, having queue times in CI results in a lot of developer downtime. So, back in 2019, we were kind of a traditional company. We're very much an on-premise company at Zenseact, since we have such big data volumes and there's a lot of network traffic and whatnot going around. So it makes a lot of sense for us being on-prem. But back then, as I said, a really traditional company, hosting our workloads in virtual machines. CI/CD were running about 700 virtual machines, really. and we kind of split them up in between small, medium, and large. But of these 700 VMs, like only 200 of them were in use at that point in time, because we needed to over-provision a whole lot to handle these really spiky workloads. But that typically led us to find ourselves in situations like this one. So as you can see, we're having the resources, but not at the right place, because we didn't have any real good way of reprovisioning it, thus leading to CI/CD queue times a whole lot. And really, it didn't matter how much we scaled. Really, we typically just pushed that issue further ahead of us. So as we kind of shifted focus then towards a whole lot more dynamic resources, and really, being able to put developers in the driver's seat without any handovers. And looking at the cloud-native ecosystems.
Yeah, so the CI team at Zenseact started exploring. So now we're going into the kind of like the nitty-gritty details of what we did. So they started looking at the build environment. So there's a lot of build tools. There's the Mavens and Ants of the Java world. There's the Makes, the CMakes, the Mesons. There's a whole bunch of different build tools that all have their kind of like pros and cons. But many of those tools that I mentioned, one of the differences towards Bazel is that they give all the power and flexibility to the end user, to the developer, to the engineer, but really doesn't give any of that power or flexibility to the build system. So Bazel takes a different approach and putting some rules or potentially constraints in how you can construct your build input. But on the flip side of that, it gives you some pretty cool capabilities. And for this talk, we'll talk about two capabilities specifically. So one is remote execution. Now, you imagine there's like 500 developers at Zenseact, and there's a really complex code base, right? We're compiling autonomous drive software and whatnot. So it's a big, complex code base with a lot of dependencies and whatnot. So compiling that code to a binary actually takes quite a bit of computational power. So imagine you're on a local laptop and you need to compile that, like a kernel, and that can potentially take a long time depending on the capacity of your machine. So the remote execution allows us to distribute that compilation or computational task into a build farm. The second piece is the cache. Now, let's imagine again, we have a large code base, many developers, everyone is building it. There's a high chance that someone has built, a large part of what you're looking for already. So what if we could store that in a cache? So we only need to compile the piece that just you changed so that we can reuse this. So these two things are really a massive improvement to both the inner loop, so when the developer is really in the zone and coding and think about how to solve their challenge, they're compiling, they're doing again, but also for the outer loop, because the outer loop, the CI system, is executing the same build system, so that can also tap into that remote execution, so tapping into the build farm, but also making use of kind of like the cache. So we only need to build 2% and it not 100%. So these two capabilities. And Bazel basically allows you to interact with the backend that implements these capabilities. And Buildbarn is the backend that implements the remote execution and the cache. So these two components were in scope or in target to deploy to OpenShift. I see that the graphic is kind of like not working at all. But anyway, so it's gray on my screen. I'll be honest, that it was pretty complicated to make sure that this was tuned and kind of like configured correctly to deploy to the OpenShift environment. But after some work, it turned to be a really awesome knot.
Well, not really. It sounds like we were really agile, and especially when it comes to technology. We were definitely not afraid of, hey, that's a good idea, let's go, let's try that. And let's fail and learn from that. And that's kind of what we did with this. And you might be able to explain a bit more why. I know now, but yeah.
Yeah, so we had actually designed the initial solution for the scale-up problem. Like, we have an application that is reaching its limits of scale-up, so we need to scale out. But that really didn't have any special performance requirements, so we built it for a virtual solution. So we were running OpenShift and ODF, containerized Ceph, on a virtual platform. So both the OpenShift, the compute, and the storage, ODF, was running on that environment. In addition, ODF, or containerized Ceph, was also running on top of software-defined storage. So we had 2 layers of software-defined replicated storage. And it turns out that your CI, it scales massively. You know, you have hundreds of cores spinning up, and all of that kind of like needs access to quick both storage and compute. And I think you said something like your virtual environment tried to accommodate that and tried to move machines around. So that introduced additional latency when we really needed to spike up really, really quickly. So we kind of like went back to the drawing board with the obvious conclusion that we're going to run on physical hardware instead. So instead of running OpenShift on virtual machines and Ceph or ODF on physical virtual machines, we moved to a physical solution. Again, the colors are really off. It's like gray boxes on my screen. Looks really nice here. And I think you guys went out and bought some really fancy hardware stuff, right?
Not really. I mean, our OpenShift cluster, or at least the cluster we're talking about here, is kind of a Frankenstein's monster. Again, we wanted to do more with less, right? We kind of just went out and took servers from various compute platforms. And I mean, OpenShift has a huge flexibility in that sense. We didn't have to care about it being the same CPU architectures and whatnot, but it was still really capable hardware, really high tier that we were able to bring into this OpenShift cluster, and it's been working really good for us since.
So after quite a bit of a while, so now we had a physical environment, we were finally able to get up and running with the Buildbarn, the cache, and the remote execution on physical hardware. I am also going to be transparent that when you move to physical hardware, that brings some interesting challenges as well, because all of the sudden nodes are massive. They have like 90 plus cores and lots of memory. So it required very specific tuning to get those workloads to perform correctly on that hardware. But I think we performed kind of cool, so there are some interesting results.
There really are. I mean, this Buildbarn and Basin and all, everything has been a huge success at Zenseact. It really it improved a lot for us and really has helped us to move towards zero faster. Building our product, complete product, is something that we do at least on average once an hour. And with this cache solution, it only takes 10 minutes. So you can imagine the efficiency gain that we're getting from this. So it's really amazing.
But I don't think you settled for that result. I believe you found that potentially there's more to do.
Exactly. I mean, I mentioned GPUs before, and GPU has been a really tricky resource for us to manage for a long time. I'm sure many of you also have GPU issues with drivers and whatnot. And the way that we've kind of provisioned GPUs to our developers is through VMs, either via pass-through, giving out a full GPU card, or half a virtual GPU card, right? But that's really difficult when you have very spiky business demand, and we often find ourselves in situations where developers were asking us for more GPUs, because we couldn't reprovision and keep up with business demand essentially. But we also noticed that the GPUs that we had really low utilization. Not when they were in use, but they weren't in use that often. I mean, developers have a lot of downtime. They might be home taking care of sick kids. They might be in a team meeting and whatnot. And then I have this other guy, hey, I want to try this out. And then I need 4 GPUs. But for us to kind of reprovision that in VMs, that's not feasible really. We're only 9 people in team infrastructure at Zenseact, so it kind of forces us to make smart solutions, right? Serving these 500 developers. But yeah, we set out to test stuff. We tested a couple of solutions, ended up with Runai, which allows us to dynamically run GPU workloads. So instead of having one GPU job at one GPU, essentially, now we're able to dynamically assign GPUs. Our developers are basically just claiming how much GPU they want, and they can also claim fractions of GPUs, which is really, really good. So many workloads that we have is actually not loading the GPU up to 100%, but most workloads are probably somewhere between 20 and 40%. That means that without this, we're wasting a whole lot of resources. And this has been a huge success. We're running this within CI now. We will continue on this track to move more GPU workloads into OpenShift here. We'll cover that a bit more later. But yeah, we made a 10 times efficiency gain here. So on average, our CI/CD workloads are using 100 GPUs. Now they're only using 10. So yeah, now I have a lot of spare GPUs out of a sudden without buying anything more. So this has been great for us, really.
Can I have one? Yeah, so we talked so far about kind of like the build system, so how we kind of like sped that up and to save both the inner loop time for a developer, but also the outer loops, kind of like the CI time. But imagine that the job time shrunk, right? So before a job, a computational task might have taken X amount of time, and now we shrunk that down massively. But what is actually orchestrating this? And a show of hands, how many of you guys have heard of Sool CI? Cool, interesting. That's actually, I was surprised. So Sool has a lot of background. There's many Sools, by the way. There's one in Ghostbusters, like the god that's gonna kill us. And there's the Sool from Netflix that is some kind of like gateway, and Sool CI, which is it's like a Jenkins, right? But Sool is a system for building, kind of like driving a CI. So it has some couple of interesting capabilities. The kind of like the headline or tagline of Sool is stop merging broken code. So again, we think about these 500 developers. They're all chugging along. They all want to contribute back to the repo. And if I submit something that actually breaks someone else, the whole company stops. So we need to find a way to stop merging broken code. And Sool has a pretty interesting capability called predictive merge. So kinda it allows us to test the future. And since this is an automotive session, it probably has a flux capacitor. I'm not sure it does, but anyway, so you have a couple of series of changes aligned that is going to be, it's sometimes merged into a repo, and Sool is basically then speculating that the first merge will actually succeed, so the second change will test itself with the first change merged to the same repo. So it's speculating that this is going to work, and it does that for the third and fourth and fifth change. And if you have 500 developers, potentially there's a lot of changes in flight. So it allows us to test all of these proposed changes in parallel as opposed to in serial. And that is a massive speed up. So a couple of things. Is this easy? How many customers worldwide do you think runs Runai, Basil, Sool CI on OpenShift bare metal? Yeah, I'm not sure. I don't know. There was a show of hand of one. So there's been quite a bit of integration challenges, right? So I think you said something like we solved one problem, but then we kind of like caused two others or found two other problems. But I think that the end results have been really interesting. And I think, how many jobs are you running? Like, how many jobs were you running a day or now?
Yeah, through Sool, the GPU jobs were about 21,000 per day being run. Yeah, really efficiently.
So again, kind of like we are able to then massively scale up the number of jobs, and that's also caused by that the computational time it takes to run each job has also shrunk. So we're able to shrink the time it takes to run a job to massively provision more jobs, basically on the same hardware. So how does the platform look like today?
Yeah, as you can see, this is a picture of our ecosystem today. Every tool set here has kind of been carefully tested through trial and error, and we ended up in something like this. Far from complete, really, but we're really happy and very proud to have ended up here just in a couple of years. Again, every tool here is carefully chosen for us to be able to increase our efficiency, being able to put our developers in the driver's seat, having full control of their infrastructure resources. As Johnny mentioned, it's have not been easy to get here. It's been tricky road. We've learned a lot throughout it, and just moving stuff to OpenShift definitely haven't solved all of our problems. It solved the problems we wanted, but also created a whole lot of new ones. But in kind of a way, these problems that we're facing now, they're much more complex. We're having a whole lot better dialogues with our developers at Zenseact, much more mature conversations going on. And yeah, yes, way more advanced. We're able to create so much more value throughout this ecosystem. And we're going to continue this journey. It's just being started. really. So talking a bit about the future and what we'll do around the... Oh, sorry. Yeah, looking back, of course. As you can see, these are quite high percentages and good numbers for us. This ecosystem has really been able to increase our output and really fulfilling our motto, helping us to get towards here a whole lot faster. I really like seeing just going from 25,000 jobs up to 100,000. I checked the numbers this morning. It looks like we're going to beat 100,000 quite well this week so far. So it's nice that the stuff is working even while I'm here. Actually, but yeah, just be able to do all of this without doing any expensive hardware expansions and all that. Of course, we could have thrown money at the problem, just bought more hardware and whatnot, but that's not good if you're counting like carbon footprints and all of that. So we're really happy to be here, really.
It would be interesting to see the electricity. Yeah, it would have been interesting to see if you had done any reduction in electricity. But anyway, so.
Oh yeah, we have. Yeah, we're looking a bit at future Zenseact. As I mentioned, we'll definitely continue on this journey, definitely. And we're going to keep a lot of the GPU use cases. GPU is an ever-increasing resource. It's often requested at Zenseact. So the benefits that we're able to do with Runai, we're going to expand a whole lot on that. Johnny talked a bit about remote execution, being able to handle local workloads. It can to some extent, but we have a lot of other GPU use cases where we can't use remote execution. Overall, we'll continue, first off, to continue to migrate workloads from VMware into OpenShift. We'll also then target these kind of local workloads. Those are also covered in our VDIs. And then specifically around GPU use cases, we mean to bring this into OpenShift using dev spaces and Runai workspaces, really, just helping our developers to kind of abstract the whole infrastructure layer, making that very, very easy for them, very standardized. They can just claim resources and then get access to these really fast data center resources, right? That's going to be a huge help for us because, yeah, we do have a lot of problems at Zenseact with them developing a whole lot of stuff locally. You can't walk the hallways without hearing a laptop's fan screaming and all that. We'll probably increase this number even more once they get access to this beefy data center hardware. We're also going to look at our deep learning environment. We have a quite big deep learning environment with DDXs and whatnot to do all of that training. We also have identified that we can gain a whole lot from hosting these DDXs as worker nodes within OpenShift. So it's definitely something we're going to look into.
Yeah, and it's one of those things that is really fantastic about coming to Summit. I'm going to do a plug for OpenShift Commons. So we were at OpenShift Commons on Monday, and one example, we meet Ervan, who's taking care of accelerators on OpenShift, and we have a great conversation about distributed learning stuff that's kind of like coming, and then we get to speak with the CTO office, emerging technology, and they talk to us about Kepler, how to actually measure and track electricity. So there's so many things that just by coming here. Oh, we had a really tricky question to Derek Carr, who's kind of like the lead architect of OpenShift. So being able to come on site to engage with the community and the engineers and the partners, that really helps us bring this solution to life, is one of the really amazing things. Yeah, I think that's it from a content perspective, and we have roughly 9-10 minutes for questions. So yeah.
I'm going to jump on the control plane one. Yes, we definitely did notice a couple of things there. Again, bringing in all of these tools and during quite short time frame. There's been a lot of integrational issues for us, and we had to work a lot with Red Hat and with Runai to kind of get this in tune. But mostly was software things that we easily can kind of fix in that way. Sorry, could you repeat the first question as well?
How many GPUs are there? 100,000 jobs?
No. So out of the 100,000 jobs. Yeah, right.
Segmentation of GPU jobs versus non-GPU jobs.
Yeah, it's a bit okay. About 40%. About 40%. Yeah.
Any more questions? Yeah, it's kind of like one interesting thing is that we're two people on stage, and by all no means does that represent the brain power that has kind of like contributed to the solution. So there's more people and teams to mention that, you know, I'm seldom the smartest person in the room, and it's definitely true at Zenseact. There's a lot of really bright and smart people. So it couldn't really have been made without the help of the wider Zenseact team, which has been an amazing journey. Yeah.
You started the presentation with the goal here is to reduce the number of deaths in traffic. Based on the job you're doing here, what are your goals there on the reduction?
Yeah.
Yeah, I mean, it's just to reach zero faster, really. I'm not aware of can any step-down plan or anything like that, really. But yeah, towards zero faster as soon as possible, really. And speed ahead towards that.
So kind of like my comment on that, obviously I work for Red Hat, so my comment. So if you look at the number of engineering drops, so that's like the deliveries, it's increased by 400%. So if we go back to the engineering loop we talked about, right? So kind of like the overall engineering loop in the beginning. That was a lot of slides. So if we can speed up a portion of this engineering loop massively, then the ability to deliver software to the car increases massively, which allows us to do more experiments to basically reach the goal. Because we kind of like an engineering effort it's a big engineering loop. We need to do something, get the result, and go back and kind of like repeat that cycle. So if we can shrink this bigger engineering loop to be very tight and fast, that's what's contributing, you know, the ability to develop faster, basically. More questions? Great questions. Yeah.
You're showing here that big group for development. And how far are you in that development of these different building blocks? Is the main focus at the moment the software factory part? And that is the starting point? Or are you also working on the other elements to combine them?
We're very much working on all of the elements, and we're far ahead in all of them. And of course, any improvements that we make within them has a huge impact. But the one that's probably the most powerful is the software part, where we can improve. But we already are up and running with over-the-air updates, the data gathering, data crunching of the raw data, and ingest of that data. We have test cars testing all around the world, specifically designed test cars. The uploads data. So this is very much up and running and very much far ahead.
So these sensors on the cars, right, the radar, LiDAR, so that generates terabytes of data, right? And so that data is getting uploaded into the data center, right? Because of the processing to
Yep.
right, like what and all that. How much data are you dealing with, and how do you manage that user on your OpenShift cluster?
It's two different environments, really. When we get to the OpenShift cluster, we're only reaping the rewards. Then we've done a lot of filtering of that data, so the data ones aren't that big. And just for us to get you're absolutely right. All of these sensors and stuff, when we do the test runs, they generate huge amounts of data. I believe we're sitting somewhere around like 150 petabytes of data, really. So, and that could easily be more. We have many teams working on kind of cleaning and categorizing it, to making sure that we only keep the most valuable data. Yeah.
And one other kind of related question, different though. So in your CI, right, continuous integration, are you doing like hardware in the loop tests as well as software in the loop simulations and stuff like that?
Yes, these are common CI jobs. Yeah, any other question? All right. Thanks a lot, everybody, for coming here, listening to this talk. And yeah, again, as Johnny said, a lot of good people being behind it. It's an honor to come here and present before you. Thanks.